This qubit virtualization is essentially applying advanced error correction techniques to our processor. We optimize for the movements, the interactions, and the processes that we need to implement error correction, so you can work with logical qubits instead of physical qubits to implement your algorithm.
It's our last episode of the year, and if I had to summarize 2024 in 2 quantum computing topics, they would be the release of the NIST PQC standards and the arrival of logical qubits. We'll be digging into the latter in this episode. I'm breaking our normal intro style here to point out that this conversation was recorded a couple of weeks before a major announcement by Atom Computing. They performed computation on 28 logical qubits with the help of Microsoft's Qubit virtualization. So I had to share that exciting news up front. Find out all the details of how that works and how many logical qubits are coming soon in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guest today is the Vice President of Research Collaborations at Atom Computing, Kristen Pudenz. Welcome to the show.
Hi, thanks for having me.
Yeah, so we recently had Krista Savor from Microsoft on, and she talked about some of the latest developments at Azure Quantum, including qubit virtualization. And I bring that up for a reason. So this technology helped create logical qubits and systems from different vendors with different quantum modalities. So we're going to explore a little bit about how qubit virtualization may accelerate the path towards fault tolerance in your company's modality, neutral atom. That said, neutral atom. Maybe you can give our listeners a light intro to what neutral atom even means, in case they haven't heard an episode before where we've talked about it.
Yeah, it's always useful for quantum computers, right? Because there are so many different modalities, and what you need to make a quantum computer at the root of the thing is really a controllable physical system that has at least 2 levels that you can access and manipulate, tangle between different qubits. For neutral atoms, the qubits that we use are exactly atoms, and we take the atoms and we trap them in the laser beam that's focused down to a very fine point. If you look that up in the literature, you'll need the term laser tweezers and find all the good work that people have done across a variety of scientific disciplines using that tool. It's been a tool not only for quantum computing and other quantum information disciplines, but people use it in biology and chemistry to hang on to small pieces of whatever they need to manipulate. So laser tweezers are well-established Nobel Prize technology, and that's how we hang on to and manipulate individual atoms. So, okay, you've got an atom, that's great. You've got it trapped, that's great. Now you need to control its state. So we choose a qubit state in the electronic structure of the neutral atom. If you look through the neutral atom literature, there are different qubits you can use. We use the nuclear spin qubit, which means that it's a very stable system. We get long coherence times out of these systems because these nuclear spin states are exceedingly well protected from environmental noise. When you have your qubit in the nuclear spin state, this is one of my favorite things about neutral atoms, and one of the reasons I'm at a neutral atom company is because all qubits have sort of a trade-off in their nature between how coherent they are, how clean they are, how long they can keep their quantum information individually, and how much they like to talk to their neighbors, and how good of a 2Q gate you can achieve, right? And the trade-off that neutral atoms have in the space is extremely favorable, because you can sit in the well-protected nuclear spin state and do most of your qubit Eileen and single qubit manipulations there. And then when you want to do a 2-qubit gate, you actually excite the electron to a high line excited state, one of these Rydberg states, and the atoms, which until this point haven't really seen each other, the Rydberg states of adjacent atoms, they overlap. You get a blockade interaction, and it is based on this blockade interaction that we create the 2-qubit gate between the 2 atoms. So it's a strong effect, and we can turn it on and off very effectively. So we have these really robust Rydberg-based 2Q gates. We also have all-to-all connectivity, because one of the cool things about laser tweezers is you can make a movable focused laser beam of light. So you can drag and drop atoms, and we can drag and drop multiple atoms at once into whatever configuration we like. And then we just put the atoms that we'd like to interact next to one another. And we activate the Ripper gates, and we get this fantastic coherence times, fantastic 2Q gates, and fantastic connectivity, configurability of the computing platform. So there are a lot of advantages to neutral atoms, and we think it's a really promising way to build and scale quantum computers.
Yeah, I was going to ask you a bit about how it compares to other modalities as far as advantages and disadvantages. It sounds like you at least started to answer that anyway, but we can dig into that a little more here. So when you say all-to-all connectivity, do you mean that at any given time they are all connected, really? Or are you talking about like a version of swapping, really, just to help the listener visualize it?
Yeah, it's not the same thing as swapping at all, because when you're doing swapping to connect qubits that are far separated and don't move in a processor, say a superconducting quantum processor, which many people are familiar with, what you're doing is you're bouncing the quantum information through n qubits that separate the two that you're interested in. What we are doing is different. We are picking up the two qubits that are far separated in space. We are bringing them physically together, and we are doing a 2-qubit gate directly on the adjacent qubits. So that's a more direct quantum interaction. The price you pay for it is the time and the fidelity and the potential for loss that you do during the movement operations. But we find that it's worth it in our systems.
Great. Yeah, I wanted to dig into that a little so people could understand, because they hear these terms and they don't really always know what's going on with the connectivity. So you mentioned also the long coherence times. That's always been impressive, right? Like some neutral atom systems, you can measure them in full seconds, let alone, anything with a modifier in front of it, like milli or whatever. Do you know what the best times you've gotten without any kind of what we're going to get to, the logical, just like in general, how long they can maintain coherence?
Yeah, so if you look at the literature that atom computing has published, we actually have a publication on our prototype machine that has tens of seconds of coherence time, and we do see tens of seconds on our commercial machines as well. So
yeah, that's wild.
That data is published, and anyone can verify it for the prototype.
Yeah, that's terrific. So now moving on to the whole idea of logical qubits, how many logical qubits have you been able to create? And then maybe you want to explain how the Microsoft Qubit virtualization works to enable them.
Yeah. Logical qubits are critical to the future of quantum computing, right? We've been working in the NIST era of quantum computing. It's been really beneficial for the field to be able to explore how small numbers of qubits can interact. What are the limits on algorithms that you can run sort of on the bare physical implementation of quantum computers? But we're at a point where it's clear that has limit, and the limit is noise. And the field has always known that and always prepared for that, right? And that's why we have the robust field of error correction. This qubit virtualization is essentially applying advanced error correction techniques to our processor. And so we optimize for the movements and the interactions and the processes that we need to implement error correction. So you can work with logical qubits instead of physical qubits to implement your algorithm. And we've sort of done all that pre-work for you. And that pre-work is important. The most important piece of what atom computing is doing together with Microsoft for qubit virtualization is the close technical working relationship between the two teams and the co-design approach that we're taking. Anyone who's done NIST work on quantum computers, or really any kind of work with a commercial processor of any kind, knows that quantum resources are precious at this point, and you have to be thoughtful about the noise and physical characteristics of the platform that you're targeting. We're doing all that careful work under the covers of the qubit virtualization, so we can offer highly performant logical qubits on the Atom Computing Microsoft hardware. I can say we are working with multiple logical qubits. I cannot tell you how many today, but I would encourage everyone to watch for updates in the space, because the technical progress is really rapid and exciting to see.
Okay, yeah. And that said, you did publish like a phase timeline of sorts. Although I don't know if it's a timeline in direction, but not with little year markers underneath it. So if we could discuss what that looks like right now. Right now, it's broken up into like levels 2 and 3. And then there's numbers of logical qubits in each. And then I didn't know if you can explain levels 2 and 3, and then maybe give us even a vague hint of what that translates to in real years. On the time.
I can give you a sort of an intuitive guideline to what you can expect. And the roadmap is useful, right? Because you can see what to expect from the systems that are coming in the future and what to expect for scaling. Scaling is hugely important for quantum computers because you need many computers, maybe not as, or many qubits, maybe not as dire a ratio as was projected in the past to implement performant logical qubits, because the codes have improved a great deal, and that's exciting to see. But nevertheless, it is the assignment of hardware providers to provide a platform that is big enough, robust enough, and performant enough to support the error correction that we will need to make very long circuits for utility scale quantum computers that are useful for some commercial application. And so when we talk about level 2 quantum systems, if you look at this roadmap, we are talking about the 1,225 qubit system that we have in Boulder right now is generation 2 and is within this level 2 resilient architecture. And then we project that within that resilient category will also fall generation 3, and that's a 10,000 qubit machine that we're projecting as the next generation of atom architecture and preparing to begin design and build of. We project in our roadmap each system generation scaling by an order of magnitude, because that's where we encounter the interesting technical challenges and the real nuts that we need to crack to do scaling to these really large machines that everybody agrees are needed for utility scale. So when we talk about these resilient machines, what we're talking about is machines that can demonstrate scientific applications and proof of promise for quantum computing, right? If you're thinking about a 1225 qubit machine, we're projecting that's going to have 10 to 50 logical qubits. The Gen 3 machine, the 10K qubit machine, we're projecting it's going to have 100 or perhaps even more logical qubits. There's a lot of room within that space, actually, of logical qubits even, to generate a scaling chart and to try to project when you think that you're gonna cross the classical curve. So these proof of promise applications that encourage us to invest in the future of quantum computing, prepare for very large generations, and some scientific knowledge that we can get maybe from magnetic problems are a good example of this, right? That we can look at problems that are smaller, but actually physically very complex, learn something new about the science and the universe from our small computational examples, and be able to feed that back into a larger computational algorithm. That's how we think about the resilient era of quantum computation. It's a really exciting time of growth that the field will get to partake in over the next several years. For level 3 scaling, this is when we think that these systems the rubber will meet the road, we'll be able to run commercial applications, we'll reach for utility scale, and we will work on problems that have value to the commercial community. So the first place we're going to look for this value is in chemistry. We think there are catalyst problems and molecule configuration problems that are really of really high value to the community. And there's a lot of literature around this that's emerging as people start to make concrete plans for how we're going to use these very large quantum computers. We also look for pointers toward optimization and machine learning at large scale that might be able to move the needle on industrial applications. So we're very excited about level 3. We have a solid roadmap to get there. One of the great things about neutral atom technology is it scales very well. You can put many, many atoms together in a vacuum cell, and there's not very much stopping you along the way. We're looking at multiple system generations for the future. If you look at the roadmap, we have not published due dates for each of our system generations. It is an ongoing research and development process, but we generally think about 2 to 3 years between system generations as an appropriate place to put a mindset.
Okay. And as you said, how you can cram a lot of qubits into a system. So are these still then being visualized as one thing? Let's say a level 3 machine, 100,000 physical qubits to get, 1,000 plus logical. Would you still see that as 100,000 of these atoms inside one, chamber, whatever you want to call it? Or are you talking about like a bunch of little ones that are somehow interconnected at that point?
Yeah, so quantum computers of all modalities live in specialized containers of limited size, right?
Mm-hmm.
And so for a superconducting quantum computer, that specialized container is the dilution refrigerator, and the main limiting factor is the amount of control signal you can get out down into the dilution refrigerator while still having it do its dilution refrigerator job of cooling the atoms or cooling the qubits to a performance state. And for an ion trap, the limit on the superconducting machines is somewhere around 1,000 qubits. The limit on an ion trap, because the ion traps, ions are great because they have more handles to hang on to with the electromagnetic properties that they have, but their specialized containers are even more limited size, and most of the projections I have seen are around 100 qubits, maybe pushing that a little bit with newer technology. For neutral atoms, we think that we can pretty comfortably get to a 100,000 qubit machine within a single vacuum cell. So the vacuum cell for neutral atoms is the specialized container of limited size, and really the factors that determine that are the what we can see through a microscope objective, right? We're always addressing laser beams to our atoms through a microscope objective. And what you can see and accurately point at through the microscope objective is sort of where you can control qubits. We're very confident that that degree of freedom is adequately satisfied. You can also think about power to make all the necessary traps, right? And we've done projections, and we think that we have some favorable power scaling characteristics that we can invoke to be able to trap 100,000 qubits at the same time. And then finally, you can think of like, well, this isn't necessarily putting them together, but for operating that machine, you think about speed of gates and movement and readout. This is something that we always talk about for atomic systems of any stripe, right? Because atoms respond more slowly than superconducting constructed qubits. And that's a double-edged sword. You can keep up with them almost certainly for large-scale error-correcting processing. But the actual speed of the computation is something you really need to think about and grapple with. And that goes into the co-design of logical qubits that we think about all the time. So we're very confident that we can realize and operate these large systems within a single vacuum cell. Gives us a great deal of connectivity between our qubits, even at large scale. We don't have these bottlenecks for interconnects. That said, we do have strategies that we think our scaling is not limited to what we can achieve in one vacuum cell. There's much more runway for neutral atoms beyond that.
And that's a three-dimensional vacuum cell, right? It's going to be stacks, like a lattice kind of.
That's a two-dimensional system. It is possible to do it in 3D, but we're looking at 2D for our roadmap 2D for at the present time.
I was curious how many.
We've played with these variables at various times of 3D and interconnects, and when that's solidified enough to be made public, we'll be sure to let you know.
Okay, but even 2D would be pretty small. It's
exciting to be in the neutral atom field because we have all these things to play with, right? The questions that we look at every day are more of, well, which promising technical direction do we think we have the bandwidth to tackle first, rather than, well, we've exhausted many and what's left, and that's an exciting place to be.
Well, you should do 4D. You should have some qubits set up now, and then in the future, come back and use them.
or just do the math to make it look like we time traveled, right?
And then release a paper saying you did time travel, or you went through a wormhole or whatever. Yeah, no, it's very easy to generate a headline with a quantum paper. Really. um, so will these logical qubits be fixed, or will there be some kind of like sliding mechanism? Like depending on the need of the circuit, when you say a range, does that mean it's always 50 logical qubits, or sometimes can it be 100 because it's logical in quotes and you don't need them to live quite so long, et cetera?
Yeah, this is a smart question because error correcting codes, I'm sure you know, usually come in families, and there are trades you can make depending on how many logical qubits you want versus how long you want them to stay coherent and what their 2Q fidelity of the encoded gate in particular you want to have, right? So part of the answer to this is co-design. We are, like I said, we're doing a lot of this detailed and physical platform oriented work up front, and we are co-designing to hit sweet spots in that trade space that are sort of appropriate for every system generation. But there may be some ability to do these trade-offs between size of logical qubits and performance. And basically, as we find sweet spots and as we architect for excellent system performance, we'll pick the appropriate alternatives in the code space to offer to people who are developing applications. So we'll try to make it as performant as possible for the community.
Yeah, because I'm assuming, which brings us to the next question, I'm assuming there's going to be a lot of abstraction to when you're coding anyway. Are these going to be available only through Azure Quantum? So would it be Q# as the go-to language that then gets translated down to your system, or will there be multiple ways to access these machines?
Yeah, so the primary access mechanism would be Azure Quantum. Mm-hmm. We will also be and are in conversations now about system sales. So we're planning for the release of systems to customers who really need a whole unit, and of course the Azure Quantum front end will be available with those systems as well. So yeah, Q# is the best friend of Azure Quantum, right? But there's also QIR, which is sort of a lower level language that many practitioners find useful. So there's a good variety of tools to interact with systems through Azure Quantum.
And will there be like an upgradable path? Like, oh, we bought this system. Can you send us some more atoms that we can like pump in? And will it be like that?
Yeah, and I mean it is a very customer focused offering, right? So so if people are looking for an upgradable system path, I encourage them to get in touch with Atom Computing, and we have those conversations with customers every day.
Yeah. It's easy to upgrade, don't trust an atom, they make up everything. So
we have that on the t-shirt, actually.
Yeah. So what kinds of scaling challenges do you expect? Like, are there other techniques being explored for logical ratios? Like, I know right now we're doing this thing with Microsoft, right? You've got that in place, but are there other things being worked on too for scaling?
Yeah, so we touched on this a little bit in the system generations when I was telling you about the limiting factors of multiple qubits in a module. So, like I said, power, speed, field of view, we think about all of this. Parallelism of system operations is another important area of technical development that we're looking at. How do you move many qubits at once and get them to all do what you want to do? Because we don't want to be waiting for this part of the processor to execute while we have this part of the processor staged and ready. We want to be able to execute algorithms in the most efficient manner that is possible on the hardware. So we're working on all of these things. What that results in is incredibly flexible hardware, right? When we execute on the internal roadmap to systematically burn down all this technical risk and implement on these features, it's kind of a dream machine for quantum computing. So we consider the Microsoft codes and the co-design that we're doing with them. This is going to be an extremely performant route to logical quantum computing, right? But that performant machine is also able to execute, especially if you have all-to-all connectivity. The universe is kind of yours as to error correction schemes and things you can execute on a quantum computer. And we expect that there will be physical layer access to the system to be able to try whatever scientific applications and error correction a customer might need to tune the system to their needs. So there's just multiple levels of how you interact with a quantum computer, and I think that's appropriate to the stage of development of the field right now.
Yeah. And it does sound like a dream setup. I mean, we are talking about atoms, right? I mean, they're not that affixed to any point in space or time, as I said, so they're pretty flexible. So back to advantage on applications. So you worked for 7 years on quantum development at Lockheed Martin. That's pretty cool. And you're old school like me. Like, you've been involved in this for more than a decade in quantum. So I don't come across too many other folks that have been working more than a decade in quantum. So I just want to ask you, did that time at Lockheed Martin prepare you in what way for building practical systems? Like, what did you learn about the real world aspects? You were working on, I assume they wanted you to come up with something practical.
Yes.
Yeah.
Yeah, they did. That's why I worked so well between me and Lockheed Martin, and I still work with the team there all the time. So I have been practically focused for quantum computing since the beginning of my career, since I got into the field. I was one of the early engineers that did my PhD in quantum computing. So I was an electrical engineer who came up through a physics group, and that was a really exciting and interesting place to be. So I've always been interested in how we can bring up applications and error correction and future-facing elements to quantum computers that connect them to the applications. Because if you build a beautiful gift and you take it to the recipient and they say, "Well, I have no use for this gift," then you've wasted a lot of time, right? And I spent much of my time at Lockheed Martin trying to close that loop and close that cycle and make quantum computing relevant for many applications. So I've been involved with commercial quantum computers since the beginning. I did my first work on the first chip that D-Wave installed outside of its laboratory of origin. And then Lockheed Martin was a great place to be because we got access to various other commercial quantum computers as they came online, and mapped applications for the future of the technology, right? So what we did largely was, I mentioned, I think, proof of promise earlier. So look for hints in early quantum computers to differentiate quantum performance from classical performance, and find how that could be useful for industrial players in the field. And that's a delicate and detail-oriented business, but a very valuable one, because then you can be ready when the technology comes online. And then, again, interacting with domain experts. I think domain expert involvement in the fields of use is absolutely critical for quantum computers, because you can, if you're really successful, you can extract a well-formed problem, and then that's a jewel for quantum computing development, and it really allows you to make an impact.
Yeah, because I mean, you hear rumors of things like $50,000 hammers when it comes to government contracting. So I can imagine what price range one of those things would be if it was a quantum hammer, right? Like, a $500 million quantum hammer. That could happen. So there's obviously a possibility that while you were at, we're going into dangerous territory here. There's a possibility that while you were at Lockheed Martin, that some projects required security clearance or would touch on projects that required security clearance. So you never really hear anything about this. This topic never gets covered. So are you allowed to say anything about how QIS kind of tangoed in that space, how it might be used in similar defense industries right now? If you have any info.
Yeah, there are many public-facing defense applications of multiple quantum technologies, actually. I worked across all of quantum information science. I managed quantum information science for Lockheed Martin for about 4 years. And so, quantum computing, there's, of course, everybody asks you immediately about the paper that launched 1,000 chips, which would be, or 1,000 PhDs, which would be Shor's algorithm and the cryptographic applications. And I think there's more to that cryptographic angle than just Shor's algorithm, but that's a source of perpetual interest in the field. And that's a good thing for the field because it allows a lot of development work to happen, right? But we also thought a lot about what I consider the three main application areas for quantum computing, which is chemistry and materials. And you can think of, there are many catalysts that would be transformative for the defense industry if you could, make fuel in a form that's more compact or efficient, say, or performance materials. If you can have lighter, stronger materials. That's something aerospace is always looking for. Electromagnetic characteristics of materials, mapping those, being able to predict what's going to happen. those are all very important for defense. So those are some of the most scientific problems in that space. Then you talk about optimization and machine learning, and boy, there are so many nails you can use those hammers for, right? Those could be very expensive hammers if they actually work well, because you can talk about production lines for optimization. You can talk about supply chains, which is something that defense around the world is perpetually interested in. You can talk about efficiently designing your processes and scheduling computation across multiple agents. So there's lots of interesting problems to dig into. That's probably the thing that I loved most about Lockheed Martin, was the breadth and the depth of expertise that you could find in any particular problem space. And that applies to other quantum technologies as well. I don't know if your podcast is more quantum computing oriented, or if you'd like to hear about others.
Yeah, I mean, we do keep it somewhat quantum computing, but yeah, I know there's like clocks and precision sensing and things like that, right? I mean, those other areas, I would imagine LM was very interested in. Yeah, that's easy. And so you didn't end up working on like UAPs or anything, trying to figure out with the quantum computer what we're seeing in the skies right now.
No, but people are interested in classification, yes.
Yeah, totally. It's funny how many times Lockheed Martin's name has come up in the past few months because of the UAP stuff. It's kind of comical. So does aerospace then represent a good path for someone? I always like to consider those who are listening that want to get into quantum in general. Would you view like the aerospace defense industries as a good career path for folks who want to have like some extra hand-holding, maybe apprenticeship? Because there aren't a lot of clearly defined, let's say, undergraduate programs or something. You learn some coding maybe. Is there like a work path inside of these industries for developing a career in QAS?
Yes, there is. And that's actually something I'm very proud of from my time at Lockheed Martin, is that we did a lot of professional development with engineers who came from adjacent technical areas to help them become quantum practitioners and help them inform the future of development for the industry, right? So most people working on quantum at LM at the time that they left, and still, because like I said, I still keep in touch with the group, they joined from adjacent fields. They learned on the job. They learned through doing. So through accessing these quantum computing systems, through, we'd always dangle carrots in particular in front of domain experts. So if one of them bit down on it, then we're like, okay, if we develop a quantum application here, we know it's really useful because this person has access to whatever fancy software Lockheed Martin bought them to solve this problem on the side, and it's not doing the trick. So we'll have a really direct comparison, right? And those direct comparisons are incredibly valuable for the field, because there's this, I'll call it a virtuous cycle, although it frustrates a lot of people in the field, where whenever you publish any result that you did on the quantum computer, especially for an application problem, immediately, probably a dozen engineers get on their laptop and they say, well, if that is the thing that you want to do, I can customize a solution for it and I can probably attack it and do it better. So, that kind of practical work, that kind of really advanced problem solving, it's exciting and it brings people into the field, and people get more capable and people see additional potential to the work that they're doing. So it's just a really nice place to live at the intersection of technology and application and be able to advance your career. Some people went on to pursue advanced degrees. Some people continue their professional development and their experience within the company. But it's a fun career path, and I think people are having nice time working on that.
Great. Yeah, so that's potentially useful to someone listening. Do you have any other career advice you'd want to give real quick before we start winding down? Maybe for women looking to enter the field?
Yeah, I mean, motivation is key, right? You got to choose a field and projects that really fascinate you, especially if you're at the entry point to the field, because you need to be intrinsically motivated to do this work. It's fascinating because it's at the edge of science and technology development. It's also frustrating because it's at the edge of science and technology development. And every week somebody's going to ask you, why should we do this on the quantum computer? Why should we focus in this area? Why should we be investing hours for you to do this problem? And you want to have a really genuine and stable and well-motivated answer for that. So Just dig into what you're really interested in. Network with your colleagues, attend conferences, maintain your professional network, especially if you're a woman or a minority in any way, with people who share your experiences, because quantum is still a pretty small pool. You will run into the same people again and again, and you will find people who can help you. And a lot of people get jobs through the network in quantum computing. So it's important to do that work, to build that network for yourself, and to find your allies. It's not an extremely diverse field, and I've heard many stories and seen some of the dark side of physics and some of the untoward behavior, because there is some culture in physics that's maybe not the best and not the most welcoming. But on top of that, I find the vast majority of the field to be very welcoming. And you, again, find those allies and lean on them and ask them to help you with your career development. And you'll find that you get more advancement than you get retractions.
Yeah, it sounds great. And before you know it, you'll end up being a decade plus person like we are. So that's in the industry.
That's right. People have to be starting all the time to maintain the pipeline, right?
That's true. It goes quick. So as a fellow decade pluser, I'll let you go with one last question. What do you think is going to be quantum computing's chat GPT moment?
Probably when people stop realizing that they're even using a quantum computer anymore, right? When it becomes such a broadly available tool, probably for optimization or machine learning, that it's just in the cloud, and whatever you're using on your classical computer or your smartphone just plugs into it to accelerate something, and instantly everything is going faster, and you don't know why, but you really appreciate it. And we get some new applications and some new capabilities that people have at their fingertips to apply to whatever interests them and whatever motivates them.
That's a great answer. And Microsoft's, of course, working towards that with their whole Azure model, right? It's a workload and you just pick what you need. So it's great that you're having such success with that model, especially for the qubit virtualization. And we'll look forward to hearing how many of those atoms you could cram into a little vacuum area, with or without time travel.
Yeah, it's an exciting time to be in the field, and we're having a great time with atom computing.
Now it's time for Coherence, the Quantum Executive Summary, where I take a moment to highlight some of the business impacts we discussed today, in case things got too nerdy at times. Let's recap. Neutral atom quantum computers use a Nobel Prize-winning technology, laser tweezers, to manipulate atoms and use them as qubits. To achieve multiple needed states for a qubit, neutral atom relies on nuclear spin states that are well protected from noise, which means the resulting qubits are resistant to decoherence and are long-lived. Forget tens of milliseconds, we mean tens of seconds. When you bring these atoms close together, their interactions create gates that also have high fidelity. You can pack many of these atoms in 2 dimensions for now, and even in 3 dimensions in the future. All these factors set the stage for error correction and building logical qubits. Moving around neutral atoms to compute with each other takes time. How can you avoid paying the cost of using multiple qubits to create logical ones? We had Microsoft talk about qubit virtualization, but basically, atom computing uses it to optimize the movements, interactions, and processes that a neutral atom system needs to implement error correction. You heard Kristen hint at an announcement in this episode, and as I said in the intro, that announcement is that they have 28 logical qubits humming away with Microsoft. There's a link to a blog post in the show notes. What does all this mean for the timeline of advantage? Atom computing's current generation 2 system has 1,225 qubits and should provide up to 50 logical qubits. The next Gen 2 system will have 10,000 qubits with over 100 logical qubits. Expect some quantum advantage papers to start popping up by then. The following Gen 3 should provide over 1,000 logical qubits. Add some interconnect and a few systems, and who knows, you might be cracking encryption. Atom computing won't say precisely when the next Gen 2 and Gen 3 systems will arrive, but achieving 28 logical qubits has been an exciting way to end the year. That does it for this episode. Thanks to Kristen Pudenz for joining to discuss atom computing. And thank you for listening, today and all year. We'll return in January with some new surprises. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on Twitter and LinkedIn. Happy holidays, and until next time, be kind and stay quantum curious.